Hello, welcome back. Let's continue with our lecture on mathematical methods. We were looking at the Cauchy integral formula. Cauchy has produced several integral formulas. We have seen most important one in which the integral over a closed contour of an analytic function is equal to 0. Then we can have several theorems which is essentially derived from the first one. They are all called Cauchy integral formulas or Cauchy integral theorems. So Cauchy seems to have produced the integral theorems one after another. So we will not give any other name to them, or we will not refer them any serial order. It is understood that one of the Cauchy's integral formula would give you the result, and it is not so difficult to figure out which one you need to use. So with that spirit, let's learn more Cauchy's theorems. This is part of course PH3105 at IISER Calcutta. Okay, the first topic we have is Cauchy-Grossad theorem for multiply connected domain. We have seen for a simply connected domain, an analytic function over a smooth contour gives zero value. In the case of domain which is not simply connected, we also have seen the theorem of continuous deformation, where we value of integral we smoothly change from one contour to another contour, and from theorem it is clear that the value should be same if the curve can be smoothly made. Now let us see what happens in the case of multiply connected domain. Let C, C1, C2 and Cn are simple closed curves with the positive orientation. Counterclockwise direction is always taken as a positive orientation, such that the curves which are given by C1, C2, Cn are interior to C, mean that they are inside the contour C, but the region interior to each of these CKs have no common points. That means the region covered by the contour C1, C2, C3 are all inside C, but they do not overlap with each other, or they do not have any common point among themselves. In such case, if the function f of z is analytic on each of these contours, and at each point interior to C and exterior to collection of all points of Ck, where k goes from 1 to n, then contour integral of f of z over the closed contour C is given as a sum k going to n contour integral over Ck f of z dz. It is merely extension of theorem which we have seen last, that is a deformation. If we have a region which is not simply connected, then we cover that with a simple curve and then deform to the contour which we have. So in this case, we don't have a single contour, we have many contour. In such case, we can simply sum it up and do the integral. So let's pictorially see with the contour which we are interested, and let f of z be defined inside. So we have several problem points. One point where function f of z is not analytic. In such case, we want to avoid such point, because so far we do not know how to handle if the function is not analytic. Future we may know. There might be other bad points which you don't even want to look at it, and some of them you want to maybe cover with the clover or fig leaf or whatever you have. In such cases, you simply remove the region around bad points or unwanted points with the hole, or you simply don't consider those points, and some of the region maybe you simply don't want to consider. And then the way to avoid this bad region or points is by constructing a contour around them with a simple contour, so that your bad region is fully within, so there is no overlap. And if you have a discrete k such unwanted regions, you can simply cover them up with k curves, each of them. It is like putting all the unwanted element behind the bars or behind the closed room, or you cover the singularity or whatever region which you don't want to peep in inside the closed contour, and then consider the region which are outside this contour Ck and inside the contour C. So you have a contour C1, C2, C3 and C4 and so on. The condition is that each of these contours should be fully within the contour C, and the contour C1, C2, C3 and so on should not have any overlap with each other. And the function f of z should be analytic in the region outside this contour Ck and inside the contour C. Then the value of the contour integral f of z dz over the contour C is given by sum k going from 1 to n integral over a contour Ck f of z dz, where k going from 1 to n. So this is merely an extension of what we have done of a deformation of the contours, and this is applicable to generally to the n contour. So we have to make sure that they don't overlap, and then we are done with it. Now we'll not go through the full proof of this. It's too much of work and doesn't lead to any new information. We have already proved one of such simple cases, and I assume that theorem can be easily generalized to general Ck. So let us take an example and work with it, so that what we are doing is useful. If we have a multiple unwanted point, we can cover them up with the contour and do the integral. So let us evaluate the integral of dz by z square plus 1, where the contour C is given by circle mod z is equal to 4. The mod z is equal to 4 is essentially means a circle of radius 4 around z is equal to 0, contour which we are interested. Now let us carefully look at the function f of z, which is 1 by z square plus 1. So is the function is analytic in the domain. We know that there is problem when the denominator goes to 0. Denominator z square plus 1 can become 0 2 point, that is at z is equal to plus or minus I, where the root of the denominator, and we have function which is not analytic. So we can use this theorem. In order to use this, we write function f of z as 1 by z square plus 1, and that can be expanded as a 1 by z plus I into z minus I, and we know that the point z is equal to plus or minus I are not analytic. In our domain, the contour which we are interested is mod z is equal to 4, that is a circle around the origin, and that we call as a contour C. Now the problematic points are z0 is equal to I and z1 is equal to minus I. These are the point at which denominator blows up. That is where the function is not analytic. So that is the point which we have to avoid. Then we construct two contours, C1 and C2, both in the same orientation as C, and then we cover these two bad points around that at z0 is equal to I and z0 is equal to minus I. Then we can use this theorem. That means integral over the contour C is given by the sum of integral over the contour C1 and C2. Since no theorem helps us to compute the integral over C1 and C2, that we can do explicitly. We are already expert in evaluating the complex integral over a circle. We have seen it in the previous example. It is a fairly trivial or a easy job to do. So in order to do that, let us rewrite the function again, f of z, using a partial fraction. We write f of z is equal to 1 by z square plus 1 as a 1 by 2i into 1 by z minus I minus 1 by 2i into 1 by z plus I. This method is usually called a partial fraction. You might have forgotten. If you remember and fresh with it, it is well and good. Often these minor details are forgotten with the vast, more interesting knowledge. So if you don't remember, just practice with the partial fraction. It is an interesting topic to do. So we have written this product as two sums, and that is where we have split the f of z as sum of two functions. Now we can integrate these two functions in this contour C or in terms of the contour C1 and C2. So this usually results in the 4 integral. The first part we'll have a 2 integral over C1 and C2, and then the second part Again, we will have a 2 integral over C1 and C2 that leads to 4 parts. So let us do it more carefully. So we have integral of this function dz by z square plus 1 over contour C. Using the partial fraction, we have already written this as a 1 by 2i into integral over contour C as a 1 by z minus I minus 1 by z plus I. So this is a result of simple partial fraction. We introduce two contours, that is circles, around z is equal to I and z is equal to minus I. We can keep the radius of circle to be a naught. Both of them are different them. At least we have to choose the radius of these contours such that there is no overlapping region over the contour C1 and C2. Once we have chosen A naught such that no overlap happens, then we can simply apply Cauchy's theorem. So we now have the integral which is written in terms of sum of two functions and in terms of sum of two contours C1 and C2. So we result in the four contours. Now we look at C1 and then we see that there is a singular point which is inside the curve C1. So we have to evaluate this. Now let's look at the second term which is completely analytic inside the contour C1. So that means we can again use one of the previous Cauchy's theorem and then say that this integral is simply 0. Now let us look at the third term. And the third term, again, the same thing happened. In the contour C1, we do not have any singular value because the singular value is at plus I. So there is no singular point. So the integral value of this function is 0. And then we left with the last term, which has a singular point inside the C2. So we have to evaluate the first term and the last term. Rest of the integrals are 0 because there is no singular point inside the given contour. Now we know we have already done this exercise with one of the examples in the previous class. So we have to evaluate this and this integral, which can be straightforward done by substituting z is equal to e to the power I theta, dz is equal to I e power I theta, and theta going from 0 to 2 pi. If you do all that, then you simply get 2 pi I. Then outside we have 2i, and that cancels out, and then these two comes with the opposite sign, and then that turns out to be 0. Even though there are singularities inside the contour C, and that integral turns out to be 0 because contribution from the curve contour C1 is exactly cancelled out by the contribution by the contour C2, resulting in 0. So once we have done an example, next thing naturally to follow is the homework problem. That is, now the homework problem is to evaluate the contour integral over a contour C given by dz by z square minus 1, where the contour C here given by the circle mod z is equal to C. So you use the same as what we have done previously. In this case, you have to look where are the singular points or where the function is not analytic and then proceed as before. This problem is much simpler than the example which we have done, which had its own complication. So I will leave you to do the problem and upload the answer on the V11. So let's continue with the Cauchy's integral formula. So we have more and more easy right on the Cauchy's integral formula. Now let f of z be analytic in a simply connected domain D. Let C be a simple closed contour lying entirely inside the domain D. Then for any point z0 within the contour, what we have is a f of z is equal to 1 by 2 pi I integral over a closed contour f of z by z minus z0 dz. So it is an interesting theorem in which you can evaluate function at a point z0 using the integral over the contour. The contour itself tell you what is inside the contour. So that is an interesting way of knowing. This is also a way of showing how some of the interesting thing happens in the physics also. If you have a charge kept inside Gaussian surface, you can know the value of the charge So this might be very similar to that. You have to see there is a factor of z minus z naught is sitting. You might want to visualize that, but I believe you are yet not familiar with some of aspects of how to solve the Laplace or Helmholtz equation. Once you are familiar with that, you will be more easily able to visualize this in terms of the physics. So let us go ahead pictorially see. We have a contour which is smooth, and we have a function f of z which is analytic inside, and we have a point z0 inside this contour. Then we can evaluate the value of function at z0 using this Cauchy's theorem. So let's quickly look at the proof. It is fairly simple since I am proving it here, so you can guess it should be simple. If it is a complicated proof, I would leave it as a exercise or allow you to read it yourself. Let D be the simply connected domain, and then we have a simple closed contour which is entirely in the domain D. Then Z0 is the point inside the contour C. Now once we have this point, let's, for the sake of simplicity, we take another point Z0 and construct a contour C1. Once we construct the contour C1, we can simply use some of the earlier Cauchy's theorems and then play around with to get value of the integral and show that if the function is analytic, then this should give f of z0. That is a simple trick. So let's start with the integral and see whether it gives the value of f of z0. So integral over contour C f of z by z minus z0 from one of the earlier Cauchy's theorem. What we have, that is exactly equal to integral over a contour C1 as given in this figure, f of z by z minus z0. If we treat this entire thing inside the integrand as a function, then we know that there is a singular point or there is a non-analytic point at z is equal to z0, and we cover it with the, or we ignore that domain completely, cover it with the fig leaf, and then construct a smooth contour to cover it, and then we have earlier construct with the patching it up the contour and all that thing you can do, or you can simply use the Cauchy's theorem, and then we know that this integral of this function is reduces to integral on the contour C1. Now all we have to do is to evaluate it explicitly, and that we can do it by taking C1 to be simple circle centered around Z0. So that is the easiest way of doing. Let us write this integral over contour C1 f of z divided by z minus z0 dz as an integral over contour C. The numerator we simply write as f of z0 plus f of z minus f of z0. That essentially means that we do nothing. So we do nothing here, but still we have an expression which is long. And numerator we already have z minus z0. Now we separate out the first term here, which is bit convenient, and then we have a second term which we are also bit familiar with. The first term gives you simply f of z0, which can be brought out. It does not take part in the integral because it is constant evaluated z is equal to z0. Then we have a contour integral over contour C1 1 by z minus z0 dz. The second term, which is interestingly what we have, is an integral over contour C1 f of z minus f of z0 divided by z minus z0. Now this looks somewhat familiar. Earlier we have done an exercise in which we have showed that integral over a contour z minus z0 dz should be equal to 2 pi I. We have shown much more general result. We have shown that 1 by z minus z0 to the power n becomes 0 if n is not equal to 1. If n is equal to 1, then you get 2 pi I. So we use that result directly here. If you interested yourself to do some donkey work, you can evaluate this. That is not general style of mathematical physics, and simply borrow the result wherever and whenever you can. The second term, which is interestingly familiar term, which is actually f of z prime. That is the first derivative. Derivative is basically f of z minus z naught divided by z minus z naught as a limiting value, z going to z naught. Now we see that that is a smooth function. We are looking at the analytic function. For an analytic function in the domain or in the neighborhood of z naught, we should have a f of z, and f of z prime should be smooth, and then Cauchy-Riemann condition should be satisfied. From that angle, what we have is a z prime is a smooth function. If it is a smooth function without any odd point, then we use Cauchy's theorem, show that that is 0. So from that, what we get is simply the contribution coming from the first term, which is equal to 2 pi I. Now we know that this integral, which we started with, we divided into two terms, and that two terms, one of them is going 0, other one is giving 2 pi I f of z naught, and that is exactly what we were looking at. We can now divide it by 2 pi, and then we prove the result what we are interested in. So this is how we use previous Cauchy's theorem to prove new Cauchy's theorem. So in fact, you can all start from the first one and systematically show whatever result you want, but you don't have to. You can say that from Cauchy's theorem you get that. So which of the Cauchy's theorem, it doesn't matter. All of them start with the first one, which says that integral over a closed contour of an analytic function with the smooth value over the contour is going 0. So then you can add various appendix to that to get more and more complicated, and that is what we have is proved that f of z is equal to 1 by 2 pi I integral over a closed contour C f of z by z minus z naught dz. So as usual, let's take a quick example. So examples are interesting way of understanding the problem. So here we have to evaluate an integral over a closed contour C. Integrand is given by a function which is z square minus 4z plus 4. It sounds very simple. If you are good at mathematics, you should be quickly able to figure out what is that exactly is. And in the denominator, what you have is a z plus I. So together we have to evaluate this integral over a contour with circle radius 2 centered at z is equal to 0. Now we have to evaluate this integral. Easiest way is to use the Cauchy's theorem. How do we use Cauchy's theorem? One, we have an analytic function on the numerator, and then we have a z minus z naught in the denominator. Once we know that, we can simply use this as a f of z and then say z minus z naught, and then that becomes a value of analytic integral at the value at the function f of z. Now identify the function f of z as a z square minus 4z plus 4, and the contour is given by mod z is equal to 2, and this function is completely analytic. And then we choose z naught is equal to minus I, which is inside this circle. Find that it is inside the contour. So then we simply have to use the Cauchy's integral theorem, which says that f of z is equal to 1 by 2 pi I, and then integral over closed contour f of z minus z naught. Then we take this value to be other side, and then we get the value of integral. Basically, we know the value of the function f of z at z naught, then multiply by 2 pi I, that should be the value of the integral. So we can use them either way. If you know the value of the function over the contour, then you can evaluate value of the function at z naught, or if you know the value of the function at z naught, you can evaluate this integral. We will use to evaluate this integral. So what we have is this integral. This should be equal to 2 pi I times f of z naught, where z naught is a minus I. So we simply substitute that and then find out that 2 pi I, 3 plus 4i, that is we have to substitute here, and then this becomes minus 1, and this becomes 3, and then that is 4i. The value of the integral is given by 2 pi into minus 4 plus 3i. So this is the value of this integral. So that is how we use the Cauchy's theorem to evaluate the integral given a value of point inside. One more example. That seems to be a lot of example. We are truly leading by example. So let's look at what is it. We have to evaluate the integral over a closed contour C of a function z by z square plus 9 dz. The contour C is given by the circle z minus 2I is equal to 4. So that means that it is a circle of a radius 4. The center is shifted to plus 2I. The function f of z is given by z square plus 9. We use our old trick. So first we look at the denominator and figure out the point at which the function can be nicely written as a z minus z naught. That is how the Cauchy's formulas can be used. So we write the denominator, which is z square plus 9, as a z minus 3I into z plus 3I. It's a simple factorization, and we have 2 points at which this is not analytic or this going to 0. So we can take z naught as plus or minus 3I. But interestingly, if we look at our contour, which is shifted a little bit, we have a 2 non-analytic point, minus I and plus I, but our circle is centered around z naught is equal to 2I. So it is slightly off center. So only one of the non-analytic point enters into our contour, other one does not. So that means we can simply ignore this and do not worry about this. So it's a no worry singular point. So we have a worrisome singular point here. So we can play our trick with Cauchy's formula. Now we look at this. Factorization is nicely done here. We rewrite the integral over contour C z by z square plus 9 dz as an integral over contour z by z plus 3I divided by z minus 3I. So the reason for doing that is that this term over this is analytic inside this contour. There is no problem, and we can take z naught as a 3I and simply use the Cauchy's formula to get the result. We write f of z as a z by z plus 3I, and then we have a integral value z naught, which is z is equal to 3I, and we can simply substitute it here. This integral is equal to 2 pi I into f of z naught, that is equal to 2 pi I of 3I. So we can substitute here. It's a fairly straightforward job, and you simply get pi times I. So that is the value of the integral over this contour and for the given function. So this is how we exploit the Cauchy's formula to evaluate integral. It looks like you have to play some smart trick each time. Each time you have to do a non-trivial factorization of your function, but it is not so difficult. By keenly looking at the contour and the singular point of the integrand, we can quickly come to the conclusion which of the Cauchy's theorem to be used and which of the values of z and z naught to be used. So it is not that hard, but it is certainly need putting pen and paper together. That means that you will have one more homework. So this week is going to be hectic with homework and a little more homework. So here you have to evaluate an integral which looks somewhat complicated, e to the power z, that's a very nice function, divided by z plus 3 minus 3z bar into dz over a contour C, which is a unit circle at z is equal to 0. So as usual, you have to solve this problem, write it nicely on a sheet of paper, write your name, number, and upload on VLearn. As a closing remark, it looks like it is a rather straightforward to extend the Cauchy's integral formula to an arbitrary differentiation. If you are interested, you can see this formula, but I will quickly flash this just enough for you to see this. You can not only evaluate the value of function, you can also evaluate the nth derivative. What you have is here n prime, or f of z differentiated n times at point z naught is given by this crazy term here, n surprise divided by 2 pi I, or n exclamation divided by 2 pi I, integral over contour C f of z divided by z minus z naught to the power n plus 1 dz. When you put n is equal to 0, you have a f of z naught is equal to n is 0, so 0 surprise is 1, I believe, and you have a 2 pi I and then integral f of z divided by z minus z naught to the power n plus 1 dz. So let me stop here and continue with the next lecture.